All right. Let's now do homework number 4, practice problem number 2. Okay, this one we have a wall, a composite wall, which means multiple different materials stacked together in parallel. Let's draw it like this. So we've got this wall. It consists of 3 different things. The first thing, item 1, is wood, it says, and it has a thickness of 2 centimeters, which I will write in meters. And it has a thermal conductivity of 110 watts per meter Kelvin. That is entirely unrealistic for wood. But here we are, doing the problem. All right, problem number 2. Piece of material number 2 is insulation. And instead of giving a thickness and a thermal conductivity, we are just given an RSI value of 5 Kelvin meters squared per watt. Remember, our value of insulation, RSI, is the equivalent in SI units. That's why it's R, like our value, SI. All right, and then item number 3 is drywall, and the drywall is 4 centimeters thick, which is 0.04 meters, and it has a thermal conductivity of 0.1 watts per meter Kelvin, which is much more realistic. Okay, we are asked to find, I've forgotten some information. The inside temperature of the home is 22 degrees Celsius. And the outside temperature of the home, T out, is 15 degrees Celsius. Ask yourself, which way is heat going to transfer? Okay, so we want to know, what is Q? The rate of heat loss. One more thing we know is that the area of the wall, so if we were to draw the entire wall, then this area, being, the area of the wall, if you were in the home looking at it, is equal to 5 meters by 3 meters, or 15 meters squared. All right, so let's do it. Analysis. All right, so we're asked to find Q. We know resistances or information to get resistance, and we know temperatures on the inside and outside. So we are going to use a thermal circuit. Hooray! So let's draw our little circuit. First we have the outside temperature node, and then there's heat conduction between T out and this temperature, which represents the temperature at the interface between these 2 materials. We're not even going to name that because it turns out we won't need to find it. Then we have the resistance to conduction of heat between this point and this point, which will be this node right here. And then finally we have more conduction, which faces resistance as it goes through this material from this point to this point, or the T of the inside of the home. So all of these resistances we'll express as the resistance of part 1, and we're running the double prime because these are going to be resistances used to find heat flux. So they're defined with the area term inside of it. Removed from it. And so the equation that will be associated with this is delta T. So the delta T between 2 points is equal to the heat flux that is moving through those points. Now remember, back to the question, which way is heat flowing? Well, we have hot inside, cold outside. Heat always flows from hot to cold. So inside to outside, we have this Q double prime. And that is going to be multiplied by some total resistance that resists the flow of heat between these 2 temperature nodes. So we need to find that total resistance. Since these resistances are in series, right, we could draw an equivalent circuit that looks like this. We have these same temperature nodes, but now only one resistance, which is R total. And that R total is just equal to each of our individual wall resistances added together in series. Okay, so let's add them up, which means we need to figure them out. R double prime, this is double prime, is equal to the length or thickness of the wall divided by the thermal conductivity of the wall. This has units of meters per watts per meter Kelvin, which when you rearrange gives Kelvin meters squared per watt. Doesn't that look familiar? That's what an RSI value unit is. So these have the same units as this single value, so we could add them together. So the resistance of wall 1 is just the length, which I've written as thickness here, 0.02 meters, divided by the thermal conductivity, 110 watts per meter Kelvin. So it's not very thick, and heat conducts very rapidly through this wall. The thermal conductivity, the larger the number, the more rapid or the less temperature drop we need for an equivalent amount of heat to move through a wall of equivalent thickness. So the larger the thermal conductivity, the less resistance we should expect, which is what we see here. Likewise, the further the heat has to travel, the larger the temperature drop we should see. We're going to add this to R2, which we don't have a thickness or a thermal conductivity, we just have a number. So we're going to add that to 5 Kelvin meters squared per watt. And we're going to add that to wall 3, which has a thickness of 0.0. Oh, man, I always hit the wrong button. Okay, which has a thickness of 0.04 meters divided by 0.1 watts per meter Kelvin. It's instructive to calculate these individually so you can see how important each part of the wall is. So first, this first calculation right here is 0.000182 plus 5 plus this is 0.4. So remember, this is resistance. So the larger the number, the greater the resistance to the flow of heat. In other words, the greater the temperature drop for an equivalent amount of heat transfer, or the less heat transfer we will have for an equivalent temperature drop. So you want a very large R value for your insulation, because the delta T in your home, at least between the inside of your home and the outside of your home, so here's you, and here's the outside, and those are usually about the same, right? You have a set point in your home, 68 degrees Fahrenheit maybe, and the outside will vary, but depending on how it varies, the more insulation you have, the less heat is allowed to escape. So we can see that this outer wood wall, which for some reason has a very large thermal conductivity, does nothing for us. It should honestly be removed if all we're doing is conserving heat. This, I'm sure, provides some structural purpose or, protects the insulation. Anyway, so adding these all together, we really get 5.04 approximately. I'm not even going to add that number in there because it makes no difference. Okay, so now that we have a resistance value, we can use this idea right here to find our Q double prime. So Q double prime equals delta T over R double prime total. Delta T is the inside minus the outside. Those are in degrees Celsius or Kelvin. Since it's a delta T, Celsius and Kelvin will be equivalent. And this is 5.04 times meters squared Celsius per watt. And this gives us the Celsius cancels watts per meter squared, which are the units of flux. So we have 7 divided by 5.04, you get 1.29 watts per meter squared. That is not the final answer, right? Look at the units. Meters squared, watts per meter squared. We want to know the total heat rate. So we have to do the rate, the total rate is equal to the heat flux times the area of the wall, which is 1.29 watts per meter squared times 15 meters squared. And that is 19.35 watts. Okay, this one was a bit more straightforward than the last one, but still some important things to cover here. Thanks for watching.